All right, another related rates problem here. This is a pretty classic type. I don't think we saw one of these in class this year, though, so definitely one that we should take a look at. So we did these light post problems back in geometry. Somebody's walking away from a lamp post, that kind of thing. So we've got a 15-foot post. Notice I put a box around it. That is constant. It's always really important to note what's constant. And then the person's height is 6 feet and the person is walking away from the pole. And you always have to come up with some kind of an equation here. And on the surface, you might think, oh, this is probably a Pythagorean theorem problem. But if you notice, they never mention the hypotenuses in the problem in any sense. So, long story short, what I realized is I have similar triangles there, just kind of going back to geometry. And so I've drawn the two similar triangles here. And I thought I'd set up a proportion, and it doesn't really matter what proportion you set up. You can set up any proportion you want here. I think I'm going to do height over base. So 6 over x is equal to 15 over y plus x. And you don't want to take a derivative of this. Okay, that's a mess. But again, if you think back to geometry, when you have a proportion, you can cross multiply and you can get an actual equation. So if we do that, we're going to have 6x plus 6y, I'm cross multiplying here, is equal to 15x. And one of the particularly interesting things here is you can subtract that 15x from both sides. You end up with a very simple equation. You end up with the equation, I'll subtract the 6x from both sides, and we'll end up with the equation that 6y is equal to 9x. Okay. And in fact, you could even simplify that down. You could simplify that down to 2y equals 3x if you'd really like to. Okay. Anyway, at some point, we need to actually put some rates in here. Okay. So where do the rates come from? Well, notice that the person is walking away from the base of the post. Okay, so this distance is changing as the person walks away. That's the rate of change of y. That's going to be a dy dt. It's the rate of change of the y variable. Okay. Meanwhile, the shadow's rate of change, we've represented the shadow with an x. Its rate of change is going to be dx dt. Okay, so I'm going to take the derivative here with respect to t, and I'm just going to see what happens. I'm just going to do this version. I'm not going to simplify it. So derivative of 6y is 6 times dy dt. Okay. Derivative of 9x is going to be 9 dx dt. And anyway, we should be able to fill all this in now. And there's not a whole lot to fill in. With the person's walking away from the pole at a rate of 4 feet per second, that means the dy dt is 4 there. So 6 times 4 is going to be 24. That's equal to 9 times dx dt. Remember, the rate of change of the shadow is what we're trying to find. So you end up with 24 ninths, or 8/3 if you'd simplified it already. And 8/3 is 2.667 feet per second. And that would be the correct answer there. So we end up getting an answer choice of B here when we put the whole thing together as the final answer. So again, any way you can write an equation might be, an area formula, a volume formula, might be a situation where you have the Pythagorean theorem, or maybe in a case where you have some similar shapes, maybe you can just set up a little similar triangle setup with a proportion and cross multiply and get your equation that way. Lots of different ways to link these things, which is why I always think they're really neat problems.